I'm starting the live stream, I think. Yeah. Um, Welcome back. This is Chill Maths on Twitch. I'm James, and today I'm going to be looking more at quadratic reciprocity, a topic which has come up before when we've tried to learn about whole numbers, and a topic that I've seen come up in other people's number theory courses. I know that if you do Promise Europe in Oxford, you spend at least some time learning about quadratic reciprocity. This is a sign that this maths is hard, or at least a sign that the maths is interesting. Right, good. Welcome to Twitch, I suppose. Hello, Maths 22222. We were just talking before the show because Maths 22222 would like this design on a mug, which they asked for last week. But this week we've remembered that you can actually do that. I don't love it. I just threw it on the thing now. I don't have a link for it. Maybe you can find it if you follow the t-shirt link and then like other products. I think I've tried to unlock a home and living section, which doesn't seem to have propagated through all of the bits of the spreadsheet. For people who are joining for the first time, I wanted to buy a t-shirt, and the easiest way to do that, in a way that I can also share it with you, is the weirdly commercial way of setting up a Spreadshirt partner shop thing, which now means that also I'm getting requests for, like, I should sell a mug or something. Hi, Mary. Hello, Charlie. 34711. Good to see you, Charlie, as well. Hola. Bienvenido a live stream. Hang on. I should ask Carlos. What is Spanish for live stream? Let's see if we can find out. So I can stay in character there. Switch, and then I'm going to go live streamed. Wow. I mean, Google Translate says transmission en vivo, which sounds a bit too literal for me. So maybe creo que es live stream. Let's see. Thank you, Mary. Live scream is what you do when the maths gets too hard. Amazing. I forgot we had native speakers with us here. Right, okay, so possibly if you keep refreshing Spreadshirt, there might be a home and living section at some point. Possibly you can get a mug. I'm not getting the mug. I've seen the mug. It's this design. I mean, possibly. I mean, I've already bought a sticker, so possibly I should find a blank mug somewhere and just apply the sticker to the mug. Disclaimer: I don't know if the stickers are washer-proof or whatever. The sticker has the pattern on, which is this nice array of pie charts. The pie charts represent the factorizations of Gaussian integers. So if you're stuck in a pinch and you need to know how to factorize a Gaussian number, you can look at your t-shirt, or by popular request, you can look at the mug that you've got. Maybe I have to get the mug. I have quite a mug-themed live stream. Right, okay. Right. Charlie has a work-related question. Go for it. You can ask if you like. Oh my goodness, Maths 222 has bought the mug. We've sold something of genus 1 rather than something of genus 3. Oh my goodness. I listed the mug about, 5 minutes? That's got to be a record for Spreadshirt. We have the best community. What's the work question, Charlie? Yeah, genus bit. Genus 3 mug would be exciting. This is a reference to the Maths Gear Genus 3 mug. Shall I advertise someone else's mug? I've searched for that in a stupid way and that has not worked. Let's see if I can find it. Someone else might find it faster than me. This one, right? This one. That's a good mark because it has the extra hole through the middle. Oh wow, you can really zoom in. There we go. Hole through the middle, which increases the genus up to 3, which lets you solve a more exciting version of the utilities problem, which they've got on the mug, because they also sell the extremely popular utilities mug thing. Right, good, okay. Other mugs are available. Right, what's going on here? What's the difference? Alright, good question, Charlie. What's the difference between Part C for people who do undergrad at Oxford compared to if I do MSc instead? At the moment, there's essentially zero difference in terms of what courses you do. You have access to all of the courses that people doing 4th year Part C maths have. It's just people coming in from other universities to do the same range of courses. There's a little bit of a move. It's possible that at some point the lists might slightly diverge. There's some push. Often we have people joining for the MMS, the master's course, with interest in other things, and there are systems at the moment for people to do or apply to do a course or an extra course from computer science or stats within the thing. But there's possibility that in the future they might diverge a little bit. Advertising law, after anything can happen in the future, but at the moment they're almost exactly the same. It's a bit like the Part 3 situation in Cambridge. So in Cambridge Part 3, as you've spotted, in Cambridge Part 3 also comes with this Master of Advanced Study thing where people turn up and do Part 3. And my understanding, maybe 10 years out of date, my understanding is that the people coming in externally to do that 4th year at Cambridge do have access to exactly the same courses as people doing the 4th year who have stayed on from Cambridge. I think there's something called, right, so scholarships. If you're a UK student, well, I'm mostly talking to Charlie, but I can talk to maths tutor to do it at the same time. I think there's a sort of student loan, but I don't know a lot about it. Let's find out. What was this? Okay, I've done a really quick Google search, and I found this gov.uk masters loan page. Disclaimer, I haven't even read the page, but because I don't work in graduate admissions, this is really lazy of me, isn't it? I don't work in graduate admissions, and it's the weekend. But I think there's a thing where people, if you live in England, get access to a similar style of funding, I think. Should I try and find out more? Funding for postgraduate loans can help you course fees and living costs while you study a postgraduate master's course, which might be how people are doing external things. I should know this sort of thing. You can apply now. You start when you get over a certain threshold. But you've said 48k. Why have you said 48k? How much are we charging external people? Is this because Oxford is actually charging loads of money to do OMS? Let me find out. This is like a little learning about graduate admissions at the weekend, because it's not my job. So this is. Sometimes I say, oh no, this is my job, let me do this during the week. This is not my job. It's closely related to my job. Right. Ooh, fully funded graduate studentships. Yes, please. Maybe that's for PhD stuff. We should probably click on that at some point. Let's have a look at the A to Z list. What are we currently charging for graduate things? Can I just go mad? Hello, Sensation Black. I think Mary asked what college I was at. I went to Trinity College, Cambridge, which is good fun. Can I find this one? Oh gosh, what are we charging for this? Is it loads? Opinions on the live stream might not represent opinions of work or... Right, okay. So isn't that more than this? Yeah, rubbish. Opinions on the live stream and opinions of me rather than opinions of even me while I'm at work or work. That number's larger than that number. That number's quite a lot larger than, well, and then this is different. Something's going on in chat where everyone's usernames have changed colour, so I might have mixed up users at some point there. Hello everyone. Right. Someone walked into the library and said, do you have any audiobooks with subtitles? You've described a normal book. Amazing. Charlie, I think they do. I think it's not as standardised as undergraduate courses. I think it does vary from course to course. Should we have a look at some other ones? What else? Ancient philosophy. Is this going to be the same numbers? Let's find out. If it's the same numbers, then I get suspicious. But it might all be the same. That's a different number, isn't it? That's not the number we just saw, because that's quite a lot larger than the other number. So different masters. That is 9 months. The previous one I clicked on, the maths one, was community finance. What we do for MCF? MCF. Click on funding. It's got different numbers. Oh right, wow. Okay. So what is that 148.6. What is going on? There's some things that you get so used to in undergraduate admissions that then you look at graduate admissions, you have to relearn things. That's a very large number compared to, for example, that number. And then the larger number is not the same either. What is going on? I mean, I do sort of know what's going on, but also, I'm sure 7k over this side. Master's courses. It's not the same as undergraduate courses. I think there may be more of a. I don't really like the phrase sort of competitive market or something here, because it makes the whole thing seem really commercial when actually opinions on the live stream might not represent opinions of the University of Oxford, because this live stream is me, not the University of Oxford. I get why, but also, free markets, capitalism, but also knowledge and sharing knowledge. It's not really my vibe. Anyway, maybe email Taylor Swift. This is the recommendation in chat. Right, did I miss anything else going on at that point? Yeah, complicated stuff at Masters. Would I suggest applying to Trinity College? I did miss a question about Trinity. Not part of work. Would you suggest applying to Trinity College, Cambridge people? Yes. You do need to do, so if you're applying to Trinity College, Cambridge, you do need to do STEP, and it is usually the case, I think, that people who have offers from Trinity do quite well on STEP. So overall, I think if you're good and you miss STEP a little bit, then other colleges might pick you up through the summer pool. But I suppose my recommendation to apply to Trinity College kind of goes hand in hand with a recommendation to do really well on STEP, which, yeah, I don't think my advice is that different from how I encourage people for Oxford. So for Oxford, I said it doesn't matter which college you apply to, because same admissions process, same course when you get there, same odds that you get admitted to Oxford because of all the shuffling around. For Cambridge, I pause a bit because of the stress on the system at the kind of summer pool. I think it all works out, and what would I know? I'm not in the room behind the scenes, but I think it all works out. But I'd be eyes open. I think if you're applying to Trinity, you're up against lots of other people who do well on STEP, and there are systems to look out for people who deserve a place at Cambridge overall, but who have applied to a college that happens to have lots of other very strong applicants. They do have systems, but for your peace of mind, knowing about that. Right, and now Charizard is in chat as well. Did you get a college? Yeah, you do get a college if you're a master's student at Oxford. I don't know the answer to that question if you ask me about Cambridge. Almost everyone at Oxford has a college. Not quite literally everyone, I have to be careful, but almost everyone at Oxford has a college, if they're a student or teaching. Yeah, I almost forgot myself. Right. Okay. Yeah, I think I'm up to speed with chat. And I've learned some stuff about graduate admissions and the way that graduate courses work in my own university. Right, Mary is having a chat with Tom Crawford about, I mean, I don't know why Tom Crawford would get to let you study at Cambridge. What does Tom Crawford have to do with Cambridge? But I'm sure if you send him a Pokemon card, that might get his attention. Hi Tom, if you're watching. Oh gosh, that's a good question. On the student side, that's very rare to be associated with multiple colleges. On the teaching side, yes, you can take multiple appointments teaching for multiple colleges. And in fact, even if people have one kind of, even if they're down to teach with one college, they might end up doing a little bit of teaching for other colleges in a kind of sharing system. So you can end up teaching for several colleges. That's not too hard. It's very hard, though, I think, be a student at several colleges. to have kind of student privileges at multiple places. It's quite hard, I think. But have some amount of teaching going on in different places. Yeah, they need loads of teaching. So teachers can. I suppose we're talking about Tom Crawford, who I think at one point had affiliations with maybe 3 colleges simultaneously when I first moved to Oxford. I think Tom was teaching at 3 places. I don't know if he's still teaching at 3. Do you want to talk about All Souls College? Tom does not work at Cambridge, as far as I know. If you find out, I'm not aware of Tom working at Cambridge currently. I think he's occasionally described as an Oxbridge person, like he's at both. But, let's talk about All Souls. All Souls. What's he doing? Oh, okay. Mary says that Tom works. Okay. All Souls is a college with no undergraduate students. Possibly no graduate students. Just fellows doing research stuff and having conversations with each other. Sounds pretty good. What does he do? What's his job? Should we go there? What's he definitely works in Oxford. Oh, Robinson. Ooh. As of October 24, undergraduate college teaching officer. Well done, Tom. I didn't know you had that. Yeah, that is a bit... Oh, we've crashed that. We didn't learn about quadratic equations for long enough. Oh, you're doing some superficials over there as well. Cool. Right, good. Well done, Tom. Okay. The remarkable went to sleep. It got bored. And the only way we can satisfy it is by learning about quadratic forms. So we were going to do that now. Last week, Maths222 asked me whether this list of properties on screen was sort of minimal in some sense. And I waved my hands and said, oh, that's a very tricky question. Who could possibly know? And then after the stream, I realised it's not a tricky question at all. The list is definitely not minimal. I mean, depends if you let me get away with... There's a different rule that they use quite a bit in the following pages, where all these things are mod p. The things upstairs are mod p. We're asked the question, is A a square mod p? So the trick that they use quite often in the following pages is that it's okay to shift that by a multiple of p. So if you ask, is 17 a square mod 3? That's kind of a silly question. We should also think about, so as well as think about 17, we should think about, is 2 a square mod 3? Those are kind of the same question. So it's a trick they use quite a lot. And it was after the stream, I realised that, technically, that means that this rule down here about -1, which they say in the text is for negative numbers, is a little bit redundant, because you always have the option of saying that this is equal to asking whether p minus 1 is a square mod p. And that's a positive number upstairs. And then you could go and use some of these rules to break it down into primes or something, and then ask these kind of sub-questions, and then hopefully work it out for separate primes. I mean, if you think you can work it out for positive numbers using these rules, then you must be able to work it out for negative numbers, because negative numbers are the same thing as positive numbers, mod p. So I don't understand why this one's here. Now, possibly I've skipped over a bit there, right? I've skipped over a bit where I said, oh, you just work it out for all the primes. I don't understand yet why these rules let us work out quadratic reciprocity. Oh, not work out whether something's a quadratic residue for all positive numbers. Or, I guess, for all numbers from 1 to p minus 1. Possibly they don't. So, Maths222 asks 2 questions, which is, are these rules minimal, and also are they complete? Are they sufficient? Do we get everywhere? There you go. Hello, me Machine Rex. You alright? Good to see you. Welcome to chat, and welcome to Chill Maths. I've learned that graduate courses charge different numbers, and I've learned that Tom Rocks Maths teaches at both Cambridge and Oxford, which I didn't know. In fact, I was pretty certain that because he worked at Oxford, that it couldn't be the case, but I've learned a fact. Learned 2 facts. Wearing my new t-shirt, have launched a new product, which is this thing but on a mug. We have sold 1 mug so far. We're doing great. Right. Maths to do with a category theory mindset, which is a place you can be. It's not obvious if these are sort of helpful rules or if they're sort of essentials. But we must have a rule for this. I suppose this flippy thing, the flippy rule, quadratic reciprocity, lets us do something which I'm thinking of a bit like Euclidean algorithm sort of thing, right? This is probably going to be in the text, or a version of this, I hope. Because this tells you if you have kind of a p less than q, which is the normal situation to be in because we're talking with modular arithmetic, so somewhere from 0 to p minus 1, not including 0, but yes, including p minus 1, I suppose. 0 is a quadratic reciprocity, whatever, anyway. So something in that range. This lets you flip it upside down, and that's interesting because you now have a large number upstairs, at which point you're allowed to divide. To do large number divided by small number, what's the remainder? Which moves us to a system with small number and the remainder. That's a step of the Euclidean algorithm. So I suppose what I'm saying is, if you give me any numbers p and q, I can use this, combined with the modular arithmetic rule that we seem to use all the time for free, to work my way down the kind of rows of the Euclidean algorithm, which I suppose I'm talking myself into this, that it'll end up being 1 somewhere, because the highest common factor of p and q is going to be 1, right? If I start with distinct primes or something, or if I only care about the prime factors of AB, surely if I have p downstairs, then if I have a factor of p upstairs at all, then I'm talking about the 0 case, so I don't care about that. So they're coprime. The thing upstairs is not a multiple of p, they're coprime, which means that eventually I'll get down to the remainder 1, highest common factor, using the Euclidean algorithm. At which point I will be asked the question, is 1 a quadratic residue mod some other number? And the answer is yes, because 1 squared is 1. Right? That will always happen. So then I'm good. Of course, I'll get some minus signs through that from all the flipping, depending on whether the things are 3 mod 4 or not. And I might have to keep splitting into primes. Yeah, my remainder might or might not be a prime number. So I might have to keep splitting into primes. But those are smaller, so I am reducing as I go down. I think I'm okay. I think that's all right. Yeah, it's kind of smaller pair somehow. I've gone fast. I've had an idea, so I'm talking quicker. Right. Mimichi Rex is learning about quintics. That's good. Good luck. Can you derive 4 using 1 and 3? Maybe. I think we're going to see a proof of 4, and it's going to be weird. Now, that's my experience of trying to learn quadratic reciprocity before, that we will see a proof, and it will be weird. And I think it's in about 20 pages' time, so I won't have to grapple with it just yet. The way this book works is we're going to do some stuff with quadratic forms first, find out that this is a great way of thinking about quadratic forms, and then get down to business and prove the fact. We had a quick look through last time, so I think we can prove it. I hope we don't need all of the others to get there, so that I can make this case. I just hope that I'm onto something with this idea that actually you don't need 2, because if you can do p minus 1 by doing some factorisation and then hoping you can do all the other primes, then you're good. And of course, in general, I don't know how to factorise p minus 1. I just know that you could factorise it. Let's have an example. Is it worth doing an example? Minus 1 mod 7? I don't quite know how I pronounce these. Maybe minus 1 over 7 or something. So minus 1 over 7 is, let's see if I can do this one, 6 over 7. So the question is 2 a quadratic residue mod 7, and is 3 a quadratic residue mod 7? And I'd like to multiply those things together. And then my plan here, right, 2 is going to be really irritating. 2 is going to be really irritating because I'm not allowed to do my flipping rule with 2. So I think I do need this. I need some combination of 3 and 4. Right, because I'm not allowed to do my flipping Euclidean algorithm thing. I'm not allowed to do the flipping Euclidean algorithm unless I have odd primes. So I need this 2-7 rule, right? Which is, I think, tells me this is plus 1. Because I am in this case where p is minus 1 mod 8. But then for 3-7, well, I don't know. So I'm going to flip it over. 3 and 7 are both 3 mod 4, so I get an extra minus sign. And then Euclidean algorithm. Euclidean algorithm says, well, you have two numbers 3 and 7, get the large one, and do the division. And you get a quotient, but really I care about the remainder, which in this case is 1. So I have a +1, I have a -1, which is commonly just written as minus sign, so I'm just going to write minus. And then a 7, I'm going to replace that with 1, because that's the remainder. 7 is 2 times 3, don't care about those, plus 1. So there we go. There are 0 divisors and even mods. Ah, yeah, it's a whole thing, isn't it? 2 times 3 equals, 0 mod 6. Prime mods are your friends. The other ones, like mod 15 as well, it's not even, but composite numbers will let you down in this way, right? If I think I know what you're talking about. But yeah, okay, good. Right, and then this thing says, is 1 a quadratic residue mod 3? And the answer is yes, it is. It's 1 squared. So I think this gives me the answer of no. -1 is not a square mod 7. So I think maybe I could slowly work this out by factorising p minus 1 for all of these different primes. This seems a bit bad. And the answer seems good. So whoever's proved this has not sat down with a list of all of the infinitely many primes of the form 1 mod 4 and done this. They've got some other idea. So is it necessary? Maybe, maybe not. Not sure at the moment. Is it worth knowing? Yes, I think so. Probably. That was a really long answer to a question that one person asked about a week ago. But that's just how the stream goes sometimes. You ask one question and then a week later you get half an answer. I don't know what most of those words mean. Sorry. It's an epi arrow. No, yeah, no. I've never learned any category theory. It shows sometimes. Sometimes I have a problem that is category theory, but I've refused to learn any category theory. So I'm sort of blind to any issues within category theory and also any solutions to my problems within category theory. I've just decided not to learn it. This is a problem. It's a bad mindset. Right, okay. Oh, I do want to do like a proper video, right? You see, I opened the box now and I have like, count them. One, morphism, I can probably bluff my way through morphism, right? But then right cancelable, nah. Sort of half an inverse. I could probably bluff my way through some of that, but I don't really want to. I should do an educational video. Yeah, I do really want to. I never really feel like I've got time. 3Billy1 Brown is also amazing and has taken loads of good topics. We talked about it a few months ago, right? Because so far nobody's made, well, correct me, but so far nobody's made a good video about that, or any video about that Pythagorean tree thing. And it took us about one live stream to understand what was going on. So maybe there's that barrier to it catching on, and that if we made a video on it, that would be good. But yeah, and I do make some videos for work. I do quite a lot of videos for work, including on things like pizza, and you've reminded me. We've done the pizza video. We've done the one about large pizzas being quite a lot larger than small pizzas. Pizza time. You see, if you get big pizza, it's like big in 2 different directions. This makes it double big. Welcome to maths. Right. If you want to see more, you can subscribe to Oxford Mathematics on social media, where occasionally I say stupid things about pizza. And compare the boxes, because the boxes are squares. Which at the time felt like quite a good way of describing it, but I think other people have done it as well. Which still means it's good, but I just felt like it was clever at the time and realised now that probably I've just seen it somewhere else. You have these 2 pizzas in boxes and you want to compare them, and the correct way to get an intuition about how big they are is to close the boxes and think about the boxes instead, because they take up the same proportion of their box each, geometrically. It felt clever at the time, because then you get a point at the box and point at the square that they fit inside. And of course, they only take up about 75% of the box, but that's all right. That was part of a series because we did pizzas, which are 2-dimensional. So large pizza, small pizza, 2D. Put some toppings on the pizza. We also did cubes and pint glasses. Hey, that reminds me, cube emoji. Has that been a cube emoji been approved? Yes, it has. Cube emote's been approved. Nice. Okay. We did a video on cubes as well, looking at the fact that to make a cube half the size, you only have to take about 20% off the width, the height, and the depth. It's 20% 3 times. It doesn't quite work like that, but that's roughly the right answer. You only have to take about 20% off, which means that if you hold 2 cubes, one twice the volume of the other, they look about the same size. And this was a series, because then, having done the 3D case about scaling and doubling, and the 2D case about scaling and doubling, we thought about doing the 1D case, where you just get some string, and you point at this piece of string that's twice as long, and you say, this piece is twice as long, which means that it is twice as long. Because scaling works. Scaling works the way that you think it should in 1D. It's sort of linear, which is the way that people tend to assume that everything works. We didn't quite make the stupid video of saying, this is twice as long. On a ruler, the middle is halfway. That is half of the whole length. Didn't quite make that video because I think it just felt like surrealist, kind of the end state. I suppose the end state is the 0-dimensional case where I'm there with like nothing. Just, you can double it and you still don't have anything. Thanks for watching. It was shrinkflation, and we also did video. We had pint glasses and stuff as well. I'm proud of the old ones; they were quite good. Future topics for learning: algebraic topology, category theory, and sieve theory. Oh, good luck me. Mary has found the ice cube. There you go. Right. Right. Everyone behaving in chat. What lectures? Oh, I'm doing Introduction to University Maths. I've got the notes down here somewhere. It's arguably what I'm supposed to be working on at my weekends, really. But I've got this introductory course. It's been running for several years. I'm slightly remixing the lecture notes. When you take over a course, you're supposed to change. Well, you're supposed to consider making minor changes only in the first year. That's the guidance I was given. Minor changes only. But I've gone through making the diagrams into TIX diagrams. So we've got some nicer Venn diagrams. Because previously they were an image, and I know how to make them with ticks. I've made myself some Venn diagrams, and I've been trying to make the stuff like definition of a function. I've been trying to work out how to do that better. So these kind of blobs, which people always draw these blobs for a set, which you can do using ticks. So it doesn't have to be an image; it could be a vector file generated by your LaTeX code, which I think is the best way to do pictures, but it is a bit of work. So I've maybe wasted too much time remaking pictures for my lectures, rather than thinking about sequencing for teaching. But you know, yeah, I should test it out, shouldn't I? At some point, I've got a round of edits that I want to do, and then maybe we'll test it on the stream. If you're learning category theory at the moment, it's possibly not the course that you need. It's the idea of the course is that you teach everyone. I just have to teach everyone set theory and notation a little bit, just basic stuff. And what's a function? Yeah, okay, maybe one day. Right, ice cube, there you go. Ice. What does that one mean, Machine Wright? Hang on a minute. 2020 celebrate. Amazing. Feels like only yesterday. Right, I think it's a new record. We've gone 35 minutes and no maths. Proceeded no pages. I haven't got no. Pretty chill. Maybe that's a definition of chill maths. There is a textbook, but I just draw pizza in the margins. Talk about pizza instead. If we reach the ultimate end state, we've spent half an hour just talking absolute nonsense. Trying to sell mugs. What am I doing? Maybe I'm the mug. Right, okay. Quadratic reciprocity. It's a good fact. We're going to see how to prove it, but only in about 20 pages. So at this rate, never. Right, okay. Yes, we all have to do introductory courses at some point. 10,000 people a day have to, if everyone learns it. Right, okay. Yes, we had this example, which we worked through. It was the whole thing. We also did our own example, didn't we? Which is good for us. And these. So what are we talking about here? Oh, yes, because the whole question about whether you can represent a number has come down to whether you can. It's come down to whether delta, the discriminant, is a quadratic residue modulo 4n, where n is the number in question. So what's this talking about then? Represents an odd prime exactly when this is positive 1. So I've missed a factor of 4 there somewhere, haven't I? Ah, no, because we had this argument to say, if you're talking about odd primes, then same question. Is it a square modulo the prime? Yeah, no, it's all fine. It's all fine, I think. So there's not a missing factor of 4 down here. Although, whatever. Okay, fine. I've got there in a different route, I think, but never mind. Okay. So using the fact which we haven't proved yet, awkward, we haven't proved that fact yet, but using that fact, we get an answer to our question of which primes can you write as the sum of two squares. This is important for the t-shirt because the primes that are the sum of the two squares are the ones that factorise into a non-trivial pie chart, whereas the ones that don't do that don't factorise. No, that is true. Good. Right. Yeah, maths 2. You're in for a treat. There is a very clever and complicated way to prove quadratic reciprocity. I've seen, because we skimmed through, we saw a picture. Yeah, maybe sequencing. You know, it's a nice day. We're having a kind of a bit of a weird chill stream. Not weird, but we're having a more chill stream than normal. Maybe I don't need to go in sequence. Because the place this wants to go is to talk about more examples of this being good. Whereas I think maybe, there's the bookmark, to talk about these more complicated cases, maybe I want to go and look at section 6.4 to find out about quadratic reciprocity. It's what we were thinking about. So maybe I do want to skip and come back and these complications. Various theorems. Yeah, okay. Maybe I'll skip this and go to 6.4. See if we can do 6.4 instead. It might make no sense, so this might be a bad idea. We've had all this kind of complexity around different discriminants, where you might have a sort of different sort of splitting. We talked about buckets before, which forms represent particular primes within all of the forms of that discriminant, which is a complicated question, which I do care about, but I mostly care about x squared plus y squared at the moment because I'm wearing this t-shirt. So I think I'm going to skip to 6.4 and see what's over there. This has happened before, that we skimmed ahead, saw something in the distant future that looks more interesting, and then tried to skip there. It doesn't always work. We will see. But let's go, I think. Let's give this a go. Section 6.4, proof of quadratic reciprocity. Partly because Maths 2 asked how to prove it. We're going to see how to prove it, I think. Yeah, start getting the tattoos in, right? Yeah, I guess one for each emote. Just in a row, like a chat message. Just blam, 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 blam. Tattoos. Straight down the arm. No, not the other side. Good thing we've got limited slots for emotes, because I've just decided that I'm getting all of them tattooed on my body. Right. Good. Okay, here's a formula that captures all of this 3 mod 4 stuff that we had going on. When can you flip them upside down and get the same answer? The answer is, well, we're looking for we're only talking about odd primes. Don't panic about square roots of -1. We're only looking at odd primes. We're going to subtract 1 and divide by 2. So if these were 1 mod 4, if either of these were 1 mod 4, we would get an even number. After subtracting 1, 0 mod 4 divided by 2, you get an even number, which would then be an even product and give us 1 to say these are the same. Only in the case that they're both 3 mod 4 do you break that. Ice. Oh, it's so warm today. I think I do need ice. Right. Okay. Only time, yeah, blah, 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 blah. Okay, 3 main steps in the proof of quadratic reciprocity, many small steps. The first is to get an explicit algebraic formula for A over P, due originally to Euler. Good. The second step is to use this formula to give a somewhat more geometric, oh, it's my favourite, somewhat more geometric interpretation. This is this kind of diagram of a big rectangle in a certain triangular pattern. Then the third step is the actual proof, using symmetry properties of the patterns of dots. And then this is the proof due to Eisenstein, which I feel like I've seen before in, I believe, Vicky Neal's number theory notes from Cambridge from 2011 sort of time. I think we looked through those at one point. Okay, about a year ago I looked through the live streams. Here we go again. Right. Yeah, we need an ice redemption where I come back with just ice. And now I've remembered the embarrassing episode 2 weeks ago where I tried to subtly eat ice without anyone noticing and did not get away with it, because you can't just subtly eat ice cubes without people noticing that something's going on. Okay. Right, we're going to use P for an odd prime, and the symbol A would always denote an arbitrary non-zero integer not divisible by P. Brilliant, those are the ones I care about. If it's 0, that's a square. Put it on a t-shirt. If it's 0, that's a square. No, stop selling out. When we write a congruence like this, it will always mean mod P, even if we're not even going to bother writing mod P. Ooh. Okay, I'll survive, I think. Euler's formula is this. A is a square mod P, even only if A to the P minus 1 over 2 is 1 mod P. It might be 1, it might be minus 1. Oh, actually, those are the two cases. It might be 1 if it is, minus 1 if it isn't. I've seen this based on, where have I seen this? We've talked about this a little bit. So to the power of P minus 1 would be Fermat's little theorem. So the cases are 1 and minus 1, and the question is how many of them? Oh, and one direction is easy. If it is a square, then Fermat's little theorem shows you that this would have to be 1. The other direction is a bit harder, but I think you can appeal to some idea about how many times it should be 1 or not. Let's find out what they say in this book that is on screen. Right. For example, for P equals 11, I find, okay, this, minus 1, yeah, great, correct values, good. Euler's formula determines the value uniquely, minus 1, 1 are not congruent, good. Not immediately obvious that the number should always be congruent to 1 and minus 1, but when we prove it, we'll see this has to be true. I think it's true from Fermat's little theorem, and something about quadratics only having at most 2 roots modulo P a prime. Okay, right. Special case for minus 1 gives you this, which is the fact we need, or at least a fact that I've claimed we might not need, but it was worth knowing after this special minus 1 thing. It's about you have a big pile of minus 1s, how many have you got? I used this in Unique last week with the case minus 1. It didn't go down very well, but we try. I thought this is the sort of fact that you could put in like lecture 3 of a Unique summer school kind of thing. There's people who are here to maybe learn a bit of number theory for the first time. You do Euclid's algorithm in the first one, and Bezout. You do a bit of modular arithmetic introduction in the second one. What's an inverse? When can you find inverses? Ooh, you use Bezout. And then the third one, I've never quite worked out what to say in the third one. I've tried various things. Last week I tried this. A couple of weeks I'll have another go, probably not saying this. If you were at Unique last week, you may have seen a one-of-a-kind Unique number theory session. The feedback was that I did too much number theory. That's right, as well as learning number theory, I'm also, weirdly, responsible for teaching a small amount of number theory to some other people. It's really like, I have to learn it fast enough that I can teach other people. It's a whole thing. Yeah, UKMT Summer School did a lot of stuff around Euclid's algorithm and Bezout. This is not a coincidence. Both of those things have almost exactly the same treatment of Euclid's algorithm and Bezout, because both the UKT Summer School and the Oxford Unique Summer School, that content was written by Vicky Neal. The thing I liked about the UKT Summer School was finding out that I'm using the same examples as them for Euclid's algorithm, because we're both using the examples that Vicky wrote down. Haven't wanted to change which examples we're using. Okay. Trying to get the Maya Taurus sequence on a t-shirt. Yeah, if almost in the images, the slide bit. Right, okay. Hello, Fogel Stream. Good to see you. Welcome to Chill Maths. It's chiller than usual. We're in danger of finding out how quadratic reciprocity works. The danger is going to be step 2. Step 2 is going to be the hard bit. We're on step 1 at the moment. Here we are. We need to find out why this is true. Why does Euler's formula tell us that this enormous power exactly corresponds to whether or not you're a square modulo p? We will find out. Yeah, I don't really know about the Chinese remainder theorem. It is important, but also you have to do, yeah, maybe that is the third one. I'm not sure it's exciting enough. I thought that is minus 1 a square number would be an exciting end to a 3-lecture course. Okay, swings and roundabouts would have been a more appropriate topic. To see why this is true, observe that this product... Oh, we are going to use Wilson's theorem. Brilliant, love it. Love a bit of Wilson's theorem. Each factor other than 1 and p minus 1 could be paired with its multiplicative inverse mod p. Oh, great. Yes, okay. This is what I did in Unique last week. And these two terms multiply together to give 1 mod p. When you do the pairing, I mean, those two give minus 1. You're just left with this. Okay, so the rule they're using here is that inside this product, you don't know where, but there is an inverse for 2. It's not 2 itself, because only 1 and p minus 1 are their own inverses modulo p. So somewhere in there is an inverse, and they'll cancel. Same for 3 and 4 and 5 and 6, and so on. Everything else is going to cancel. The only things that won't get cancelled are these terms at the start and the end, because they are their own multiplicative inverses, and they only appear once. And then, yeah, right, okay, so it's 1 mod 4. This is the good way around. And right, okay, I've never seen someone do Wilson's theorem before Fermat's little theorem, but here we are, I have now. So Wilson's theorem first, p minus 1 factorial is minus 1 mod p. And now Fermat's little theorem as a follow-on. You take all of these numbers and you multiply them all together. Yeah, they are in some order. The numbers 1 to p minus 1. We'll call that the cancellation property. Okay. Suppose this is the same set, so multiply all together and you're good. You get exactly the right number of a's, and the rest of the stuff cancels because it has a multiplicative inverse. Good, this has suddenly turned into last week's Unique course. Good. Right, so maybe I should do quadratic reciprocity as the third lecture. I should not do that. Okay, first case is easy. It's the case where a is equal to x squared, and then this power that we're looking at is actually x to the p minus 1. So it is 1, Fermat's little theorem. Good, that's the thing I said out loud, previous page. Hooray. Okay, both sides 1. The other case is that it's not. Observe first that the congruence has a solution y mod p. Yeah, since x has an inverse, so we can just do that. Moreover, the solution y is unique mod p. Since this, we're fine, this is group theory, hooray. Since we are in the case that a is not a square mod p, the solution, like that, satisfies y is not congruent to x. So for each y and x, what are we doing here? Thus the numbers like this are divided up into p minus 1 pairs, like this, ones that multiply together to give a. Oh, this is weird. What did I think they were going to do? So I thought they were going to do a counting argument or something to say how many of these you have, but then you need a fact about how many roots you expect polynomials to have. So one approach is to interpret x to the p minus 1 over 2 minus 1 to interpret this as a polynomial which has a certain number of roots. How many roots do you think it's got? Well, probably p minus 1 over 2, and we've already found. Oh, do we know that we found them? No, maybe we don't. Maybe we don't. Well, there you go. This will tell us how many at most we have. And then similarly with a plus sign. So once you've decided they're either plus 1 or minus 1, you know you must get at most p minus 1 over 2 of each, and you've got to get p minus 1 of these things overall, so it must be max number of each. But to do that way, you need some theory about polynomials over modulo prime, which I don't think we have. Sounds overpowered. New set. I squared is again. Yeah. Right, good. I'm catching up with chat. I forgot to look at chat for a while. Okay. I don't entirely regret looking at chats, but chat's so keen on other sorts of maths, which is good to see. It's Chill Maths Sunday. We can do any sort of maths. What's the plan here? We're pairing up the numbers into products that give A. I know that none of these are paired with themselves because A is not a square. So we can pair them all up. This is a bit too clever for me. You can pair them all up into ones that are and aren't. The rule here, the unique number that multiplies by this to give A. Presumably we're now going to multiply kind of all of them together. Yeah, all of them together because they all give A when you multiply them together. That's pretty clever. Can't we be a bit more explicit than this though? It was quite vague. I know the other ones are vague as well. This is a new idea for me. Oh, Wilson's theorem again. Okay, this is a bit clever for me. No, it's good though. So you take all of the numbers, and then the idea is that I have this big product, which gives -1, and I know that some pairs give me A. For example, 1 times A. Which other ones do? 2 times something is A. They're kind of the same idea almost. None of them leave the same remainder on multiplication by A. I think we're calling this the cancellation property. That's the idea. On multiplication by A, that if you have this, then since A has a multiplicative inverse, mod P, because A is co-prime to P, since A has a multiplicative inverse, you can multiply by it, and then X is Y. X is equal to Y mod P. I'm not sure how much of that theory we've built in this textbook. I did just skip 20 pages. I guess I need 2 lectures of unique number theory here. I need Euclid Bezout in order to generate my inverses and do my little proof that you always have an inverse mod P if you're co-prime to P. This is kind of, I think we're calling it the cancellation property here, to say when you multiply these things by A. Please. Is that cheating by saying A has a unique multiplicative inverse? I guess so. I guess I am, yeah. What was their argument? Was their argument better? Multiply the inverse, yeah. Yeah, that is their argument, to multiply by the inverse. Yeah, and maybe we should do 2 lines in here. One quite complicated line using Bezout to generate a inverse, and then a uniqueness proof. So that's kind of existence. Bezout actually gives you an algorithm to generate inverses. Uniqueness, which I've spelled funny. Uniqueness would be something like if A, and this is quite a fun proof that I've seen definitely somewhere. If A has 2 inverses, call them B and C. Consider BAC. BAC, well, on the one hand, it cancels like this to give C, and on the other hand, it cancels like that to give B. These are both mod P. So you can cancel it in 2 different ways. You can force it to choose. It's like, oh, I'll give you BAC. Are you going to cancel with the B, or are you going to cancel with C? Both of them, really? In that case, you're left with C, or you're left with B. And those have got to be equivalent. So your 2 inverses are actually congruent, mod P. So there's a classic uniqueness thing there. I assume there are 2 and show they're equal. Yeah, right, okay, I'm supposed to do this with category theory. Cool. I'll just sit over here with Bezout and my standard uniqueness proofs and my, right, okay. Not learning any category theory. I've just decided. I've made a choice. Right, okay. There's some danger that if we do this joke for long enough that chat will ask us to actually do category theory, and then I will have to learn category theory as a kind of educational thing. You can explain it in chat, of course. Good. Category theory is a 4th year course at Oxford. The stream is not sponsored by Oxford, but if you'd like to learn some category theory, 4th year at Oxford has got a course on category theory currently. Oh God, Mary. You don't know what you're asking for. No. Oh, yeah, well, yes, you do. You're asking for chat to learn it. Chat to learn it to you. Good. This seems clever. I was expecting something like an understanding of. Have we already got whether or not 1 is a quadratic? No, that was an application of it. That was a special case. We have not thought about -1. Because I sort of think if -1 isn't a square, then I think you can take. If you have a single known non-square, yeah, you can take all of your squares and multiply them by your non-square. There's this rule, isn't there? So what would I do here? I do like this pairing argument, I've decided. It's just clever, and you get to use Wilson's theorem again. But could I do something with... I mean, it was better than this, because we know how many of these things there are. If you think about the roots of polynomials, if you're allowed to do that, then if you know theory about polynomials over a prime, then you know how many of these things there are. So it shouldn't just be I paired them all up and it just worked for this value of a. So what have I got? For squares, it's obviously good. And 1 is a square. So then if a is not a square, do you want to say take a and multiply by all of your squares and you get lots of non-squares? No, what am I doing though? I need to talk about a to the p minus 1 over 2. Maybe I do have to do something like this. Excuse me. Yeah, okay, so we're avoiding talking about roots of polynomials, and we've got a kind of more fun way of pairing them up and getting a power of a. Right. Okay, good. Like it. Haven't seen this before. I think this is a bit exclamation mark. Okay. Good. We're done. Consequence is the multiplicative property. Oh, like this. Consequence because powers work like that. That's good. That's a proof of property 1, I think. Oh, and property 2, because that was the one about -1. Or was that actually property 3? No, that's probably 2. Because we've got that -1 fact as a kind of special case by thinking about a big pile of -1s, -1 to the power of p minus 1 over 2. Pretty good. Okay. What else? So, step 2, time for a big rectangle. I've grappled with the big rectangle before. I think we tried to make a Desmos thing. Maybe we'll have another go. It's about to be 5 o'clock though, so we're going to have a look. Don't tell me to drink the tea yet. We're going to have a look and try and take it all in, have a cup of tea, and then come back and go through step by step. Geometric terms. P units wide and A units high. I have no idea what this has got to do with quadratic residues though. The picture shows this for 7, 5. Is 5 a square mod 7? Hard question. Interesting points that lie strictly in the interior of the rectangle, whose coordinates are integers. Lattice points. The number of lattice points is this many. The diagonal does not pass through any of these, since we assume the... Okay. Since there are no interior lattice points on the diagonal, half of them are above and half of them are below. This is an interesting sphere, it's odd, which makes p minus 1 even. Good. Yes, good. A more refined question in more classes: how many lattice points below the diagonal have even coordinate? How many have odd coordinate? No guarantee that these two numbers must be equal. Okay. So look at the lattice points below the diagonal. Of them have even x coordinates. And then we're going to do some arguing or something. Right. Okay. The way that E varies with A seems somewhat unpredictable, but it is totally related to whether A is a quadratic residue mod P, we're told. The simple relationship between E and this is that much, that it is just captured in how many points with even x coordinates lie below this line, interior T. So 7 here, so the answer is no. Mary says it's tea time. Right, so here's a picture. We've got lots of lines going on, which is interesting. 1, 2, 3, 4, 5, 6, 7, 8, 9 in this case. is 6 a quadratic residue mod? 7. You count the points, it's 9. Ah, so these different lines are looking at different cases for how big the rectangle is. Below this line, how many points do you have? And as you bring this line down, the number decreases, and whether or not it's odd or even changes. So odd, odd, even, even. But if you have this larger picture down here, then it's very complicated. As you move down, you change how many points with an even x coordinate underneath the line. Right, good, okay. We're going to have a formula for E. It's going to be a mess, like this. And we're going to use the division algorithm to try and think about what this is. We're going to come back and go through slowly, don't worry. We're speeding through so I can go and have a break to make a cup of tea. Oh my goodness. We've got this quantity R of U, the remainders, which I've been ignoring. And we're going to add these all up or something. My goodness. Okay. Look at the remainders. How distinct is U varies. Oh my goodness. Is S a function as well? It just keeps going forever. This is the next hour of my life, isn't it? Step 2. So here's a congruence, which then on the right, that looks close to Wilson, but not quite. Can we stick a minus sign on to get Wilson? Maybe that doesn't help. This product, anyway, never mind. Cancelling this gives this much, and then this is precisely what we want, because then we're done, right? Both the factors are plus minus 1 mod p, and their product is 1, so it must be equal mod p. Good. We're using Euler's formula from before, so previously we convinced ourselves that Euler's formula told us whether things are quadratic residues or not. A new idea here is that this complicated thing, counting even points under the line, gives us quadratic residues as well. Step 3 is going to be to look at focusing on A, odd prime distinct from P, which, my goodness. Okay, right, so we're going to come back after a quick break, and we're going to think quite hard about, it's just a page and a half, I think. It's just a page and a half. There's a little bit down here. To define E as a sum. And then one page about remainders, which looks quite scary, but we'll try really hard, because at the bottom, at this point, it's definitely doing the same thing as the Euler's formula thing for quadratic residues. Right, okay. Okay, tea break, I think. Cup of tea, possibly. Oh, it's very warm. I do love tea. What a challenge. Okay, I'll be back in a couple of minutes with a cup of tea at this point here. If you hang around, you might see an ad. You're welcome to go and make a cup of tea, get a glass of water. We've got at least a couple of minutes for my kettle to boil. I'm committing to the kettle, I think. I'll see you back here in a couple of minutes. If you see an advert, it does eventually support charity one day. Right, see you in a minute or two with tea. I'm back, I think. Yeah, I think I am. Could be back. I've been recommended a category theory book. It's not exactly respecting my choices not to learn category theory, but I did say that was a problem. I'll write down the name. I'll meet you halfway. I'll write down the name of the book. Categories for the working mathematician. Which is not quite me, is it? Because I'm just a mathematician for fun. There's other people out there doing hard maths work, like right at the coalface. I'm just here for good times. It would be like categories for the casual, chill mathematician. Categories for the interested amateur. It's the first ever category theory book I can. If I have to. Right, okay. I sort of get the impression category theory is a relatively new thing, but I know nothing about category theory, so maybe this is good for me. Ice cubes! Right. It's a good kettle. It's one where, okay, if you're looking for a quick kettle, you can get this type where the whole base of the kettle, inside the kettle, the whole base of the kettle is heating element. So rather than having just an immersed heating element, the whole base is the heating element. That's very, very fast because it's heating quite a lot of water all at once. The speed of my kettle is a big part of the success of chill maths, because it means I can get back here and talk absolute nonsense about kettles rather than getting on with maths. Right, we've got an hour, I think, more or less, and here is what we're going to do. We're going to read this page in a bit, which seems like what we normally do, right? Formula for E. Okay. The segment of the vertical line x equals u between the x-axis and the line has length. Let's see if I believe this. That looks like a gradient of the line multiplied by u. I think I do believe this. A is the height, p is the width. Great. UA over p, height. I'm going to write out the word height so I remind myself it's the height. I'm kind of particularly interested in even values of even u is the ones I'm particularly interested in. That's not a condition for that, that's just me reminding myself that even values of u I care about times a over p. Okay, actual fraction this time, good. Actual fraction. Not one of these. The genre symbols. Right, okay. So if u is a positive integer, the number of lattice points on this line segment is the floor, because it has some length. Okay, yep, fine. Length 1 and a bit, fine, you get 1. Length 2 and a bit. Length 2 and a bit. For this line, you get 2. Okay, great. So floor, you have to round up. Good. If we add up these, I'm doing the easy bit very slowly. Add these up, and then we're good. Okay, over even numbers. Numbers up to p minus 1. Okay. Have we met the UCAM TMUG before? The UCAM TMUG is from the Team Maths Challenge National Final. It says London, Monday 3rd of July, 2006. So it's coming up to its 20-year anniversary. It's just past its 19th anniversary. Mugs are great, aren't they? I didn't realise I'd had this long. So coming up to its 20th anniversary, it has a map of Königsberg, a dodecahedron, and 2 chess pieces, because it was associated with a task to look into Hamiltonian paths and cycles and bridges of Königsberg. I don't think we won. I think we were in the national final back in 2006. They gave the mug to my teacher. My teacher didn't want it, so I got it. Right. That's when I did the Team Maths Challenge as a child. Okay. Oh no, I've dated the live stream. Gosh, it's 20 years old. It's probably the mug I've had the longest. I shouldn't think about that. I'll get too precious about it and then I'll be extra sad when it eventually breaks. Just save myself that by not thinking. Right, way to compute this is to apply the division algorithm. You would like to know how large that is. Is it about 3 or 4? That would be good to know. Dividing p into UA to obtain this as the quotient with a remainder that we denote remainder of U. So can I write that little formula for this or something? RU is, well, hang on. So RU is something UA minus UA over P or something. So you take away the floor, take away the floor, or maybe the remainder is that. Maybe you're dividing P into UA. So maybe UA is equal to Q lots of P plus R of U. Maybe. Let's have a look at the next page. Oh yes, this much. Okay, and then there's the quotient. Oh, I should have paid more attention. There's the quotient. It goes there. And the remainder is there. Don't worry about dividing by P. Right. Okay, how's this going? So that's an integer, that's P. The formula of this implies that this has the same parity as R of U. Ooh, we only care about parity today because we're just trying to count how many minus ones we've got in a big pile. The final answer is going to be minus 1 to the power of E. So we only really care about whether E is even or odd. You might expect it to be even, for it is called E. You might expect it to be 2.7, for it is called E. But it might be an odd number or an even number. I only actually care about what it is modulo 2. Okay. I hadn't seen that coming, though we start throwing stuff away, right? So we only care about parity. Since U is even, why is U even? Well, we're only looking at the even x coordinates, even numbers, and P is odd. Right, even number on the left. This product might be odd if this is odd, in which case that would be odd. And it might be even if this is even, in which case that would be even. So these have the same parity. Hence this has the same parity as that. We only actually care about this sum as parity, so we only actually care about this. The number can be computed by just doing this. So comment here, we only care about parity of E. So we're allowed to do this sort of thing, to just look at these remainders. This is an interesting device here. You have even number, not the same. You have even equals odd times A plus B, and the inference is that these have the same parity. I'm trying to rewrite this to see if it's something that I recognise, like a shape I recognise, but I don't think it is. I mean, it's true. I can check both cases. Maybe I'm supposed to think, hang on, let's think mod 2 very quickly. 0 equals 1 times A plus B. Yeah, okay. Mod 2, it looks a bit less exciting, doesn't it? So A is negative B, which is the same thing as B mod 2. Okay, moral of the story, work mod 2. Mod 2 makes things easier. Right, okay. Last expression in mind, we will focus our attention on the remainders, yes please. Because we're just adding them. No flaws or anything. Well, I don't know what they are. Okay, so we've replaced one mystery with another mystery. It's strictly between 0 and P. Yes, it's a remainder and can be either even or odd. Terrible. But in both cases, we can say that this thing is congruent to an even number in the interval 0p. Since if this is odd, so is that. And then adding p gives an even number. Right, okay. Odd numbers and even numbers are congruent to each other in this world. Modulo p. What on earth are we doing? We'll find out in a minute, but what on earth are we doing? Thus there is always an even number between that's congruent to all of that, but we've put in this. Did I care about this RU out at the front? I'm not sure I did. It might be odd or even, and that's my whole question, is whether it's odd or even, because I'm going to add all these things up. But I've seen later on there might be some cancelling going on. Anyway, even number SU between this that's congruent to this. I'm just going to quickly write that out. SU is congruent to, and then for some reason we've got this R of U in here as well, mod P, always mod P. Quickly rewrite that. Okay. I've opened a window because it's really hot today, he says, drinking tea. Genuinely drinking tea this time, not like sometimes. There's a car alarm or some sort of toy alarm going off in the distance. Really sorry if that's ruining your Twitch chillness. Harry can hear it, but it's being nice about it. So there you go. Right. That's the way of squaring the circle between really, really hot in here and I've got a cup of tea. How can I solve this? I do need the ice. Ice always comes back to ice, keeping it chill, even on a hot day. Right, okay. Since no two numbers in this interval are congruent, so you have this even number. Right. Okay. What are we doing? Key fact about these even numbers is they're all distinct as u varies over different even numbers. That seems a bit too much to believe, doesn't it? They're all distinct. For suppose that we have SU equals SV for another even number, so this is a bit wow. Suppose we have this for another even number. So then R of U must be plus or minus R of E, because we don't know what hijinks you've got up to where you might have... Do I know what's going on here? Well, no, not really. I don't know what's going on at all. Oh, these things are RUs. SU is RU up to some minus signs, and SV is RV up to minus signs. So this is not as deep as it looks, which implies that this, in view of the equation 1 above. Oh, right, we're going all the way back. So if these things agree up to a plus or minus sign, no, I'm still lost. Where do we go? We're going all the way back up there? In view of equation 1, right, correct, okay. Multiple of P. Right, multiple of P, of course, the point of the remainder was that it's the same thing, modulo P, as UA. So go all the way back up here, and then cancel the A. Oh, this is a bit fiddly, isn't it? Cancel the A from both sides. I feel like I'm going to get to the point where I understand every line, but not at all what's going on. If we get different things for each of these, because broadly speaking, if you give me different things here, so there's this fact that we already saw that I don't like U, XA and YA aren't congruent mod P, so have different remainders. That's a different way of saying it, but we're actually looking at what those remainders are. And I still don't know why we've done this, but I'll carry on with the puzzle. We're talking about whether this, with some extra minus signs, right, whether these remainders are the same as each other or not. So no, because the remainders are something to do with whether the original numbers were the same and they're just different multiples of A. We've got these kind of columns here for different multiples of A. Good. Only looking at the evens. Is this one of those ones in Vicky Neal's notes or somebody's notes? There were lots of cases where we looked at a particular subset. I think we looked at some really hard notes at one point, which generalised it to the fact where you don't just look at odd and even numbers, you look at any subset or something crazy. It was really hard. I don't think that was Vicky Neal's notes, actually. Anyway. Right. Okay. Let's move on. I feel like we're going to do this a couple of times. I'm still going too fast. I'm also talking too fast. It's supposed to be chill. Cancel the A from both sides to get this. Can't have U equals minus V because the number between 0 and P that is congruent to the minus V is P minus V. So we would have U as P minus V, which is impossible since U and V are even. P is odd. That's a weird way of saying it. They're both even numbers. Is that a weird way of saying it? Yeah. No, that's all right. U and minus V, I'd rely on the idea that those are both even numbers as well. You can't have even numbers. Different by P. Oh, no, okay, you have to go into this because they could differ by a multiple of P. Okay, you have to do this quite precisely then. Fine, okay. Just going to do something. I was going to do something sloppy, but to try and take a shortcut here, but no, I realise why they're doing this so carefully. It's not always the case that even numbers fail to differ by a multiple of p. You can have even numbers that differ by a multiple of p, but these even numbers are quite small. They're quite close to 0, so they can't differ by a multiple of p. In particular, between 0 and p, like this. Yeah, we're using the fact that u is between 0 and p. So there isn't space for a difference of 2p, which would be an even difference that's a multiple of p. Okay. Not quite space for a difference of 2p, just. Right, okay, must have u is plus p, since these numbers are strictly between 0 and p. So they're all distinct. Okay, amazing. So it kind of goes back to where they came from. Okay, good. Different remainders. And also allowing for these minus signs don't cause any clashes because we were only talking about even numbers. This is the bit where we're using the fact that we're only looking at the even numbers, because for some reason I don't just want to look at the remainders. We've put all these minus signs in, and that's fine. This is looking like this might be a clever idea that we've had to get away with. All of this paragraph is convincing me that it's fine, sort of. We're getting lots of distinct numbers. This is going to be a classic multiply them all together and you've got the list in a different order. It's that trick, isn't it? So this is a very clever idea, I'm guessing now. I can see stuff coming up with a big product. Very clever idea that we've had to justify that this doesn't ruin everything. Often you have a clever idea, but it ruins everything. You don't make any progress because your clever idea actually mapped everything to number 1 or something. Anyway, maybe that's just me. Consider the product of all of these as U ranges. Okay, fine, here we go. Written out, it looks like this, including all of these extra minus signs that we've got hanging around. Maybe those are the bits that I wanted, actually. Maybe it's the factor of R down here, which is making them all different. That's kind of cool. I want these minus signs because I'm aiming for Euler's formula, right? I'm aiming for a big pile of minus ones. But I've got these in here, which causes all of these terms to be different. By equation 1, we have that this remainder is congruent to UA, so we get these. On the other hand, by the definition of these numbers SU, the product, here it is, the product is congruent to these. There are just these, and they are all distinct even numbers, so they are a rearrangement of these even numbers. There you go. So it's the same sort of structure as what we've had before, where we say, aha, we've got all of the even numbers just in a different order. All of the numbers you wanted just in a different order. And I think this is why we saw a very general proof of this in somebody else's lecture notes at one point, because the proof we saw before and the proof we're looking at now are almost exactly the same, I think, except there's more work in the second one to justify that these things are different, which maybe generalizes nicely. I don't know how, but maybe generalizes nicely. And the idea again is to multiply everything together. Okay, well, here's the big product, but presumably we're now done, I would hope, because these things give you, is that the right number of minus ones? This is R of P minus 1, and I wanted to sum all of these, so I want this big pile of minus ones, but I've also got R of 2, R of 4, and so on. Those are all distinct. I don't think they're all even, not the R's. Oh, but we know what the R's are. They're even multiples of A. Oh, so I'm going to get some A to the P minus 1 over 2 as well. Good, okay. So those are just the even numbers. These contain the even numbers. Right, good, here we are. Okay, so down at the end of this page, we now get our kind of punchline that this product that we carefully made with the remainders in as well as the minus signs, that shuffles around. This shuffles around the even numbers. No, it's not quite. You've multiplied all of them by A this time. You've multiplied all of them by A and some number of minus signs, but you've got the even numbers on the left and you've got all the even numbers on the right. They all cancel and then you're good. Because then you've got the big pile of minus signs that you wanted, but you've also got A to the P minus 1 over 2. And Euler's formula tells us whether that's 1 or minus 1. And then you move it over the other side. Okay, so that was slightly too fast again, and then this just says we're done. Okay, we're not going to move on to the step 3 yet. I'm going to do that one more time. This time I can kind of see what the idea is supposed to be a little bit more, I think. Noisy outside. Right, half an hour. Let's go. And you've made a Desmos graph. Let's have a quick look at the Desmos graph. Quick look at the Desmos graph. What is this? Oh my goodness. No, I don't know what this is. Oh, right. Okay, so you've asked me. You're looking at the square of x. You're taking x mod q. X mod q. So you're looking at the number x. So this graph is periodic with period q, I think. Good. And you're squaring it. And if it's actually equal to mod p in q, for some fixed p, p is varying over time, but if you have some value of p in mind, so you want to know whether 11 is a, or let's pick smaller, but you want to know if 3 is a quadratic residue, then this slightly mad approach from Twitch chat is check all possible values of x. It looks like we've set this up so it's all real values of x, just in case. Check whether they square to give. What is this outside mod sign doing? Oh no, check whether they square to give the same thing as p mod q. Can we do? I would do. I think. Is this the same thing as naive question? Sorry, but if I do x squared minus p mod q. Oh yeah, okay. So I've messed that up. Why didn't that work? I think this agrees on the integers, but it's not good otherwise. No, I've ended up somewhere totally different. What are you doing? Well, I'm going to converge on this in the end, aren't I? Right, good. Okay. Right, okay. Oh, a ladybird. A little ladybird has come to visit. It's not doing us any harm, it can stay there. Right. Okay. Oh no, it's lovely. Right. Rerunning this argument again. Looking at these. I'm going to try and doodle on the diagram this time. Let's take the top line for the case where it's 12 for square mod 13. The answer is going to turn out to be yes. Oh gosh, is 12 a square mod 13? Yes, because 5 squared is 25. Minus 1 is a square mod 13. And the argument is going to be that there are 36 coloured in 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 1, 2, 3, 4, 5, 6. But instead of counting them, I'm just going to look at the odd and evenness. Yes. Also a road. We're going to look at. So what have we been talking about then? Remainders. Maybe I should calculate the remainders for these even numbers. So these are my even numbers, e. Maybe I should calculate the remainders. So in each case, this is a challenge. I'm taking a equals 12, p is 13, and I'm looking at the remainder when you multiply a. Here we go. A times e, which is called u down here. Maybe I should call it u. U on this axis, and r of u then. R of u. Okay, so r of u tells me the remainder when you divide by p, a times u. So 24 is 12 times 2 is 24, which leaves remainder 11 when you divide by 13. 4 times 12 is 48, which leaves remainder 3 when you divide by 13. No. 48, which leaves remainder. Oh, my 13 times table is not that strong. 38, 52, so -4. So -4. -4 is the same thing as 9. 6 times 12 is 60, which leaves a remainder -5 when you divide by 13, which is 6. 8 times 12 is massive. What am I doing? 96, which when you divide by 13 leaves a remainder I don't want to know, but 96 over 13 has some remainder. Maybe we should start doing these properly. 6. How many is that? About 7 because it's 91, so remainder 5. Remainder 5 in this case. 10 times 12 is 120. Should I be adding? Maybe I should be adding. So I've got, in this case, 7 and 5/13. And in each case, I'm adding on another 2 lots of 12 is 24. So I'm adding on another 24/13. So the remainder should be going up by a predictable amount. Doesn't look like I'm getting these right because I don't have a linear pattern to these. It's a lively neighbourhood. I should be getting a linear sequence, right? Because I'm just increasing my multiples of a, so some of these are wrong. Fun. Can I fix this by just changing that to a 7? Yes, I could. So this is the tricky one where it was 6 times 12 is 72. I don't know what I said out loud, but it's 72. Does that leave a remainder 7 when you divide by 13? Yes, it does. Okay, fine. Found a pattern. Good. Got there in the end. Okay, so we've got some remainders, and then, oh my goodness, the thing that we're asked to calculate is SU, which is an even number congruent to -1 to the r to the u, r times r to u. Oh gosh, I don't know about this. So if RU is odd, you put an odd number of minus signs on it, and then you're asking for an even number. So I think this is just going to give me like a list of even numbers in order, isn't it? After all of that, my shuffling is just going to be -11 is congruent to 2 mod 13, -9, because it's odd, so you get some minus sign. -9 is congruent to 4, and there's just going to be the even numbers in order. So I was hoping to demonstrate this nice shuffling effect, but in fact I've just got the even numbers in order for these numbers SU. But they have all turned out to be even, and I kind of get that it's unique. Okay. Not a great example in the end. What a shame. We try. All of that calculation, and then it turned out to be I was demonstrating the shuffle even numbers stay still. Okay. So, right, what did that help me with, if anything? So these remainders can't be congruent because the products aren't congruent, and you're looking at the remainders modulo p. So you get different remainders, and then you do this weird switch where you put lots of minus signs on, but you insist that you write down an even number between 0 and p that it's congruent to, which is unique, and there's no repeats. Because I suppose, well, over here, the repeats might come from two genuinely equal things, but no, that doesn't happen because things don't have the same remainder. Or it might come from two different things where you put, I don't know, one of them was odd, one of them was even, and then you put more minus signs on one, so you ended up in the same place, which is impossible because if they had different parities, yes, I think I'm going to do this in more of a forwards direction. So, you know, we had to work all the way back down here to p being odd. I'd like to go forwards, which is something like if r of u and r of v are both the same parity as each other, then you've been instructed to put the same number of minus signs on. So they were distinct before, different remainders, so they'll be distinct now. They haven't become the same by putting these minus signs on. You put the same number of minus signs on. And if the r and u and r and v were different parities, then fine, you've been instructed to put a minus sign on, but you haven't now. Putting the minus sign on increases it. Here we go. Putting the minus sign on increases it by an even number. Right? putting a minus sign on increases it by an even number. Because to get from R of V to get from minus R of V to positive R of V, you increase it by 2RV. Right, okay, I prefer this forwards direction. So you had two things that, okay, if they have the same parity, then I've instructed you to put some minus signs on, either, depending on the parity, but the same if they were the same parity. If they're different parities, then the minus signs instruct you to increase one of them. Not increase it? No, not quite. The remainders are in a particular range. Mumble. The remainders are in a particular range. So if they have different parities, then one of them will be flipped negative. The one that's odd will be flipped negative, but increasing it by 2RV doesn't change its parity. Oh, no, don't love it, not quite. I've realised that you can talk about the difference here in terms of increasing. I'm not sure I love it though as a way to describe this. Let's try one more time. So if R of U and R of V have different parities, could that happen? It didn't happen in my example, but I suppose maybe it could happen in general. That R of U and R of V have different parities. They're multiplied by different numbers of minus signs. And now suppose that they're the same. Well, suppose they're the same mod P. Well, that would have to be, the way to get there would have to be that you increase this one by 2 R of V to get it back in range. And I suppose they're the same. Well, they started with different parities. The thing starts off with different parities, and now you just took this one and increased by an even number, and now you're saying they have the same parity? It's not quite there, but I think that kind of argument is how I would phrase it. Okay, right. Okay, so we've got this argument, they're all different. And then the piece de resistance, the exciting step is to multiply them all together, which is just one of those clever things, I think. I've seen it happen a few times now, so there's something going on there. But to just multiply them all together is really good. Because this operation, what are we actually doing here? So we're taking even numbers, right? They're even numbers, so we're kind of taking an even number, x, just for the set of even numbers, an even number, and we're sending it to a times -1 to the power of r of x. I'll think about that in a second, times x. So multiplying by quite a lot of stuff. And possibly adding on twice that to get it into range again. Okay. I think there's some way to think about this of just like there's some particular functions and you're acting on the set of even numbers and you're just permuting them, I think. It's tiny. The English language, we have stolen many phrases, including piece de resistance as a thing that we say, right? But it kind of counts as English. We've stolen so many words from so many places. That's why English is such a fun language. It's got so many things going on. It's not speaking French, it's English, but with theft. Good, okay. Yeah, cool phrase your language has got there, I think. Our language would like that too. Boff. Right. We've permuted the even numbers, and then when you write them all down, you get, on the one hand, loads of minus signs and loads of 8. Right, okay, that was not too bad. That's not too bad in the end. I just need to remember this idea that you take the remainders of all the even numbers multiplied by a, remainders of all the even numbers multiplied by a, and you multiply together remainder times that many minus signs. It's a complicated proof, really, isn't it? Such a complicated proof. Right, let's push on. I think we've got 20 minutes on the clock. I think we have a chance of talking specifically about the odd case where P and Q are odd numbers. And our aim is going to be to flip P and Q, to talk from a sideways rectangle to a tall rectangle by doing a reflection in the line y equals x, or something like that, to exchange P and Q. And oh my goodness, we're going to have to think about 1 mod 4 and 3 mod 4. No, we're not. We're going to have to think about these stacks of odd and even dots and counting oddness and evenness. How long's this bit going to be? So it's going to be talking very carefully about how many points there are. Oh, well, like, not too bad so far. Okay, we'll get there. And then here's a square. So we've just got a page and a bit to go. Here we go. Right, okay. Specialise. Odd prime q distinct from p. Here's a lattice. And I remember they were saying to count the ones underneath. But now we know that this number a, before it was anything, now we know it's odd. So there's going to be some parity to talk about this bit. I can kind of see what they're going to do. Okay. So the question about whether q... Oh, was that q up there? Yes, so previously it was a over p, and now we're thinking about q over p. So q is the height, to start off with at least. This q is, I think this is q equals 11, p equals 17. Okay, to start off with. E is the number, sorry for the scroll there, that was quite messy. E is the number of lattice points, sorry for the mouse as well, that's been there for ages. E is the number of lattice points with even x coordinate inside the rectangle and below the diagonal. Okay, deep breath. Suppose that we divide the rectangle into 2 equal halves, separated by this line. Okay, 2 smaller triangles, yep, I saw them. And then is it okay to count the ones above? These smaller triangles are shaded triangles. The lower small triangle L, and the upper small triangle U, and the L and U. Right, so I think they're going to try and convince me that L plus U is the thing, or the parity of L plus U is the thing that we had before. Or small L plus, the parity of small L plus small U. Enunciate clearly. Right. Note that U has the same parity, yes, here it comes, as the number of lattice points with even x coordinates in the interior of the quadrilateral below U. That's such a long sentence. In the right half of the rectangle, it's still going. Right half of the rectangle, so each column of lattice points, I thought it would do this, each column of the lattice has q minus 1 point in it, which is even. So the 2 parts split below the line and above the line. We care about the bit below the line, but the bit above has the same parity. E has the same parity as L plus U. Good. Okay, minus 1 to the E is the same thing as minus 1 to the L plus U. Right, the next thing to notice is that rotating the triangle U by 180 degrees about the centre of the rectangle, where's it going? Carries it onto the triangle L. Rotating the triangle U by 180 degrees. Oh, I've got to go and have a look at this. Rotating the triangle by 180 degrees about the midpoint, I guess. Moves it over there. So you get 4, 3, 1, 4, 3, 1 in both cases. So L and U look like they must be equal, which means the power must be even, which means that the answer must be 1. There's a special case, which we will hit in a second. Rotation takes the lattice points with an even x coordinate onto lattice points inside L with odd x coordinates. Oh no. Centre of the rectangle. Is the centre of the rectangle... Yeah, it is at 8.5. 8.5, 5.5. That's where I put it. 8.5, 5.5. That is p minus 1 over 2 and q minus 1 over 2. And we're thinking about whether that is... Oh, no, it's p over 2 and q over 2 for the centre. Bit of geometry here. We're doing a rotation. Good. Carries the rectangle onto the triangle. The rotation takes the lattice points inside U with even x coordinate onto the lattice points inside L with odd x coordinates. I missed this. So even coordinates. Right, okay, not the squares. Not the squares. We were supposed to be counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I regret this dot. Down here. And then a whole load more. But the rotation here sends these points, which are not on an interesting x coordinate, they're on 9, sends them here. Okay, so the sum of L plus U is going to be all of the points inside this triangle, which I can kind of see is going to be something that we can calculate. So let's go. Right. obtain this formula. T is the total number of lattice points inside the triangle. L, down here. Okay, all of them. So we mapped some of them onto there. Okay, reversing the roles of P and Q, we can also say that that is T prime, where T prime is the... Okay, so we do the other way around. Sort of want to make an animation of the rotation. Not really, though, because the rotation is kind of the easiest bit to understand. The hard bit is going to be the... Oh my goodness. Reversing the roles. So this, where T prime is the number of lattice points inside the triangle. L prime, with edges on the diagonal of the rectangle. The horizontal line y equals q over 2. And the y-axis. What a description. Y is q over 2. Can we have this in a picture? Y equals q over 2. So kind of similarly, are they describing this one? I think they must be. Points over there. Oh my goodness, look, but it's going to be perfect. It's going to be so good. P minus 1 over 2, Q minus 1 over 2 is going to be a relevant product for this size of this rectangle. Number of lattice points in the interior of the small rectangle. Let's read this again. The horizontal... with edges on the diagonal of the rectangle, that's that line in the middle. Why is there no picture for this one? The horizontal line y equals q over 2, that's the halfway up line, and the y-axis, that's the left side. So the lattice, you end up with a product for all of the things down here. In the picture, this is 1 mod 4, and that's 3 mod 4. So the number of dots in this bottom left corner, not including the edges, I think, so just including this stuff. 1, 2, 3, 4, 5, 6, 7, 8 is even. Oh, there's a number line down here I could have read. 8 is even, so the number of dots in this box is 8. And then the remarkable thing is that the parity of the dots down here, the ones with boxes around have come from over there. The number of dots in this bit of the triangle tells you whether or not Q is a quadratic residue mod P, and the number of dots in that bit of the rectangle tells you whether P is a quadratic residue mod Q. That's adorable. That's really good. And then, depending on the size of the rectangle, the overall total might or might not be even or odd. That's really funny. Okay. Yeah, sorry, I mentioned a rotation, and I was thinking Desmos, and then I thought, no, don't actually go and do that. That's the easy bit. The kind of rotation is the easy bit. The hard bit is everything in step 2 to justify that this number of dots means anything at all. Much less clear. It's a key proof, right? It takes these vertical stacks of dots, and since we only care about the parity, we can do some tricks to talk about these dots instead. That does it 2 different ways to get 2 different bits of this rectangle, and the products have become relevant. This slightly silly looking formula for the product P over Q, Q over P, Legendre symbols. This slightly silly looking stack of -1s is a -1 for each dot in this rectangle. With, okay, maybe you have an odd number below and they're both not squares, or you have an even number below and that one is a square. And then maybe you have an even number overall or not. Whether or not you have an even number overall depends on whether these things is either of them 1, 1, 4. Am I going to make a Desmos animation? Not sure. It's kind of like animating the last step. You could have a really crystal clear understanding of this bit, of why the dots add up, the kind of geometry of it, to say this way around we have this. Maybe the thing I'd like to see, I suppose, and I'm still not sure we should do this, is this diagram that I'm looking at only shows me Q over P and shows me the rotation for that. I wonder if there's a nice thing going on for how the rotation looks for the other way around. So I haven't really thought about the other way around, but I suppose it is. There was the proof that I saw before that tried to explain it like this, and I found it very confusing, to also count the even numbered rows. But again, to split, I suppose it would be the top half. Oh, I should stop. Oh, there we go. Activate line mode. I should stop. I try to count these horizontal things as well, and then split them up. I suppose it would rotate round. What would it do? So, switching the roles of P and Q is like a reflection, and then you're looking at even values here and counting up to the line. I guess that one's not under the line at the moment. So you would have these even numbers, and you'd be looking at these. For P over Q, Legendre symbol. And then what does the transformation look like? I have some of the rows here, and I suppose I stop looking at these rows and I look instead at these bits. We're talking about odd primes. So we're talking about odd primes. So this way is P minus 1 is even as well, and then this bit of triangle rotates in the same manner that the grey triangles rotate together, rotate on top of each other to give one entire picture. This one rotates around to give the other half of the dots inside this picture, so it's kind of a nice odd even split. Maybe it motivates the odd even split. That picture is quite confusing now because I've got things going on in different directions, which is kind of a problem and really hampered my understanding of it last time round. I think I like breaking it down to the steps like they've done in this description. So I'm just going to tidy this up and have another look at it. Ooh. Somebody's excited for quadratic residues. Okay. Okay. So, square boxes. Okay. Don't love the square boxes. I don't think they're referenced in the chat either. It's a very nice day. Everyone is outside making some noise, or inside making some live streams. Between us, we'll be fine. Bless them all. It's so chill. Right, okay. So, this is actually quite good news for me, because I quite like this geometry sort of thing at the end. I think it's a really nice picture. Odd, odd. And spinning it around to pair them up with this kind of parity argument for why you can look at those ones instead of these ones, which you shouldn't do the first time around. You should, I think, look at the ones underneath. Oh, yeah. Remarkable have updated. So now does straight lines if you wait for them. And it does, I'm very excited about this. Circles? Oh no, you have to hold down. Pop. Look at that. It pops into a circle. And squares. Or rectangles. You can rotate them. It's such a toy. Look at that. I can draw rectangles now without really trying. And ellipses, which is actually quite bad because quite often I circle something and I don't necessarily want it to pop into an ellipse, but occasionally it will pop to be an ellipse, which is only sometimes what I wanted. Remarkable. Not sponsored, believe it or not, but we have been using this one tablet that lets you write on PDFs but doesn't have the internet, crucially. This has been my go-to for almost 2 years now, which has been very good. Right. Could have done the ice cube like that, but then it wouldn't be so wonky. It's quite small, isn't it? I need to zoom it in a little bit. It's very small. That's because I took a screenshot, and the screenshot was slightly too small for Twitch. So I padded it with some just blank space around the outside, and you can really tell. I haven't got away with that. It says ice cube if you look really close, but okay, we might do a little zoom in. Right, okay. So step 3 has turned out to be fine, as predicted. Step 2 is the hard one. Yeah, you carry around loads of books. It's like the Kindle Dream, except you can also doodle on them. The Kindle Dream, sort of, in this world, taking its the dream being you can look at loads of PDFs. They're good devices, I think. Not sponsored. Remarkable. If you're watching, then wow, you've waited 2 years to get in touch, but you should get in touch. Stop trying to sell out. Goodness me. Right, okay. What am I doing? I think I'm going to have another look at step 2 for the last 5 minutes of the stream. If anybody wants anything else from this. Because I've got a nice mental image of step 3 moving around. I don't need to see things rotating in Desmos, I think. P minus 1 over 2, Q minus 1 over 2 has turned out to be relevant, so I just need more of an idea about what on earth is going on here. It's this stuff where suddenly out of nowhere, not an ellipse, minus 1 to the r remainder is relevant. And the fact that we're doing so is it, why have we done this? If this was odd, so is that, and then adding p gives an even number. You can say that anything is congruent to an even number. So this is not, the first time you read this, it sounds like they're saying you have to put in these minus signs so that it will be congruent to an even number. You know, R of u, there's a kind of split here where R of u, this is true, lies strictly between 0 and b, and it could be either even or odd. That's true, because if we're talking about congruences, then there's sort of no such thing as even and odd modulo p. Yeah, there you go. There's no such thing as even and odd modulo p, because well, you would like them to alternate, but you go round. If you add p, then you get back to the same place, and that's an odd number of adds. Okay. So we have to be really careful talking about odd or even numbers in a modulo p world, but I think they're doing it. Right, cool. Okay. Like 2 numbers in this interval. There's also always an even number that's congruent to this. So can I find some relevance? I guess they've thought about this a lot, and they would give me some geometrical relevance. They love giving me geometrical relevance of things. They would give me some geometrical relevance of S of u if they could, right? We've got these remainders for the products, which is kind of precisely what we've been doing, isn't it? For that proof of Fermat's Little theorem. It's not written out explicitly, but you have to think about the remainders. Maybe it was written out explicitly and I missed it. You have to think about the remainders so that you can say that literally this list comes back again. Mod PM could be anything. Beep, beep, beep. Right. Can I introduce yourself as Mr. Chill on the work stream? I just don't think I will. I think actually that's a sign that I'm doing quite well to separate the brands. Why is it Mr. Chill anyway? Right, okay. I think we are reaching the end of today's live stream. It's been a good one. We've seen proof of quadratic reciprocity, where I think my challenge for remembering this ever again is the idea that you take even numbers, you multiply by a, and then you multiply them by some minus signs. I feel pretty close to working out why the minus signs are there, where the number of minus signs is, so a remainder is like 2a over p multiplied by p. Yeah, the remainder is like 2a take away that. The remainder is that, take away p, 2a over p. That's the remainder. R of 2. Do I mean that? R of u, yeah, R of u for ua on the left. So that's a formula, I suppose. Which is almost always the same sort of, well, no, not almost always, about half the time, I guess. The same as just doing minus 1 to the 2a. Extra minus signs. And this is just going to shuffle around the even numbers. Do I definitely think, oh, right, okay, if you force it to be, what's the rule going to be here then? So, right, we want even numbers. We want even numbers. And when you multiply by a, you might not get an even number because there's no such thing as even numbers modulo p. So when you multiply by a and bring it back down to find the remainder, you might get an odd number. which might happen. If you do, then I think about half of them are odd. For the odd ones, I would like you to it's not precisely those, is it? Yeah, no, so the remainder has the same parity as the remainder has the same parity as remainder has the same parity as the quotient or something mad. Right, yeah, all along we've been trying to count the points underneath, so you have to think about that as well. You have to think about the definition of E in here as well. You can't just have this as a mapping all the even numbers around. You also have to remember that this thing, the sum of the remainders, or minus one to the sum of the remainders, actually has some relevance for counting these points. What does it? I mean, who says you have to think about this geometrically? We're going to think about it geometrically in step 3. But maybe there's a more abstract way to talk about these. If you copy out this formula here with u instead of 2, and you put it in here, then you just get this fact that you can prove without doing any geometry. You don't have to draw these triangles. You just get there. That's a lot of ice cubes. Ice cubes in chat. Right. Okay. Well, we know what here's the emote that was used most this month is going to be at the end of the month. We found the one that's fun to spam. It's not that fun to spam. All the text ones are not that fun to spam quite a lot. But we now have one that is actually, I guess, it's kind of fun to spam a lot. Maybe not. Maybe that's kind of the same emotion as ha, whereas kind of a whole army of the little ice cube guys, kind of a different. A whole army of the little ice cube guys kind of sends a different message to just one ice cube. I'm not sure what the message is, but there's a lot of them. Mean Machine Rex says fire, attempting to fight off all of the ice. Right, good, okay. I think it's officially, whatever it is, it's a different vibe. I'll finish my tea. I think we're finishing the stream as well. It's been another weird one. Always the way with chill maths. If you want a normal way to learn quadratic reciprocity, well, there's so many normal ways to learn quadratic reciprocity. For example, you could download this book, which is Hatcher's Topology of Numbers. Hatcher's cool and has put their textbook on their website, along with notes and things. You can get it there. So if you wanted to learn this without the Twitch dimension, that's an option available to you. Until next week. Oh, Mario wants 1 minute. Well, I'll fill for a minute if you like. Until next week, we've got a proof of quadratic reciprocity now, which is pretty good. We're going to go back 20 pages though. I think is this the end of section 6.4? It could be, might as well be. Ooh, no, we're going to prove property 3. Maybe we'll do this next time. Property 3. Ooh, special case of lattice point counting. Ooh, count some lattice points for different primes p when you get an odd or even number of points under the line. And it seems like, oh, right, okay, that seems like quite a powerful way of approaching this in these even columns only. And then we've got the end of section 6.4, which is also the end of section 6. So I think next challenge is to go back, and now we've seen a proof of quadratic reciprocity, we're going to do this a little bit. We'll do this a little bit. No, I'm just going to read it because it looks really easy. I've got to suck it in because it looks really easy. Geometric interpretation, let's go. When A is 2, so this is as high as we're going, which here's that fact. E is the number of lattice points inside that long rectangle, such a long boy, having even x coordinate and underneath a line. We're showing here lots of different lines for lots of different primes. 3, 5, 7. 9's not a prime. 11, 13. Lots of different odd numbers. Okay. Well, maybe this pattern works in general. Who knows? Another way to describe E. We said it had to be prime anywhere in our proof below. Yes, we definitely said it had to be prime because we're trying to do a cancellation property. Never mind. Yes, I'm very suspicious about our cancellation property in these cases. Never mind. Okay. Another way to describe E is to say it's equal to the number of even integers in the interval from P over 2 to P. Yes, on the right-hand side, which is where under the line lives, because we're ignoring the outsides of the rectangle, so we only seem to care about this middle bit. And the line is just the diagonal, so we're looking on the right. We do not need to assume that P is prime in order to count these, just that P is odd, so that it doesn't go through a point in the middle. In which case, well, it's like half of them, isn't it? Sloppy. Let's see what they say more precisely here. One can see that the pattern is just looking at the figure. Each time P increases by 2, there is one more even number at the right end of the interval. Oh, I see. 1, 1, 2, 2, 3, 3, 4, 4. Okay, great. So when is this even and when is this odd? Well, it takes ages to change, but it's odd here and here. So for 3 and 5 mod 8, you have to wait ages for this pattern to repeat. It's every 4 odd numbers. Okay, so that's why they've included 9 and 15, to just look at this pattern of how many dots there are, which doesn't care if you're prime or not, and has a nice pattern to it. Okay, there you go then. Parity of E depends only on the value of P mod 8, as in the table. And it just keeps going, because as you keep moving right, as you keep getting wider, you add on extra points sometimes. Okay, that's pretty nice. I should probably count them properly, shouldn't we? Number of even numbers from P over 2 to P, when P is odd. So, what's a more formal way to do that? I suppose I would split into cases or something. I would say if P over 2 plus a half is even, then I know where my even numbers are. Am I also going to worry about whether P is odd? So then I have the count is something like P minus P over 2. No, that's stupid. Wait. So I have to get from P plus 1 over 2 all the way up to P minus 1. Oh, that's such a fence post error kind of place, isn't it? So I have to go P minus 1 is the last even number, minus P over 2 plus a half is the first one. So actually I need to add 1 if I'm doing my counting very carefully, and also divide by 2 because only every other one is divided by 2 over here or something. No, this is terrible. What a disaster. How many 2's? So you got that difference, which is even. Oh my goodness. This is such a disaster. Divide by 2, but then add 1 for fence post reasons. So measure the distance here between these even numbers. Divide by 2, but then remember, you have an even number every 2, and you have 1 at each end of fence posts. So add 1. Fence post errors everywhere you look. That is the same thing as P minus, I want to say 3 over 4, but plus 1, which is the same thing as P plus 1 over 4. So that looks to me to be, well, depending on what P is mod 8, whether or not. I know, maybe this is better. Just look at the pattern and see what's going on, because fence posts are included in the pattern so far. So whoever counted to 1, 1, 2, 2, 3, 3, 4, 4 was counting carefully with the fence posts included. 1, 2, 3, 4, including this. So I'm trying to calculate this distance, and then divide by 2, and then think, oh gosh, the distance is 6, so there are 4 fence posts. You divide by 2 first, and then add 1. Goodness me. Okay, so what have I said then? If P is if P plus 1 over 2 is even, so this thing says what on earth does this say? If P plus 1, if P is 3 mod 4, it's this case. The first ones I want to think about, like 17. So if P is 3 mod 4, then here's the halfway point, and then you see an even number, so I can do my measuring. So if P is 3 mod 4, then you get a number like this, which is something that's 4 mod 4 divided by 4, so goodness knows, which is, so this is even if P is congruent to, and now I've got to go to mod 8 because I'm dividing by 4 and I still care whether this is even or odd. So this is even if P, so it could be 3 mod 4, but do I have 3 mod 8? 3 mod 8 would be nice because then when I divide by 4 I still have an even number. 3 mod 8. And then there's this other case where if P over 2 plus 1/2 is odd, which is the case where P is congruent to 1 mod 4, then 2, you add 1, you get 2 mod 4, you divide by 2, you get an odd number. If P is 1 mod 4, then we have a different number because my fence post now starts, like in the case with 15, where my fence post sits, like in the case with, 17 is 1 mod 4. What on earth am I talking about? Oh, I think I may have labelled everything wrong, chat, but never mind. When 17 is actually 1 mod 4 and the thing starts here, so I should do the same thing, but with P plus 3 over 2 instead of P plus 1/2. So P minus 1 minus P over 2 plus 3 over 2 minus 2, add the fence post back on again. We get, dare I say, P minus 1 over 4, because I've subtracted an extra 1 in here, which is then an extra 2 after I multiply 2 mod by 2. Bit sloppy, let's see if I get away with it. Which is even if, right, P is 1 mod 4, and that looks good. Even if P is 1 mod 8, maybe? Not quite. So I got this one right, and I got this one wrong, because my plan is to add 1 and divide by 4. So I don't want 3 mod 8, that's bad. 3 mod 8 is the case where you add 1 and you get something that is odd after you divide it by 4. I wanted 7 in here. That's my only mistake ever. 7 mod 8 is the correct sort of 3 mod 4. Oh my goodness, because then when you add 1. Okay, I regret doing it properly. Doing it properly is slow. Spotting the pattern, fast. Should do it like that. Right, good. Okay. You all heard the plane? Right, good. I love airplane noises. Maybe we should keep the window open all the time for some kind of like interesting texture to the stream, a little background noise. We got there in the end. We got a 7 over here, we got a 1 down there. These are the cases, plus and minus 1 mod 8. Yeah, I can see why they just spotted a pattern. Good. Mathematicians love patterns. We're going to call it there. I think I've done the extra 1 minute that Mary wanted. We've done the extra minute that Mary wanted. Time to call it. Thanks all for joining in. I'll see you next week for, oh goodness knows, some sort of quadratic form stuff, right? We've taken a break from any quadratic forms to really understand quadratic reciprocity, which I think maybe we've understood more than ever before. So I'm excited. That is, by the way, property 3 in here, property 3 done, and up here at the top of the page, it's property 2 done. Quick pause for me to try and memorise property 3. 2 is a square mod P if you're, after much calculation, 2 is a square mod P if and only if you are 1 or 7 mod 8. 7 or 1 mod 8, I'm going to say, to help me remember it, how I saw it. Right, cool. See you next week. Have a pleasant rest of your weekend, and yeah, maybe see some of you on the work stream later this week, some sort of geometry or trigonometry, I think, where we'll be in the other mode, where we do talk about work, and things are a bit less chaotic. It's weird, isn't it, that my real life could be more chaotic than my work life. I think most people like it the other way around. Does the chaos work with the chill branding? Who knows? Puzzles for another day. And I'll finish with Maths222's quote, which has just gone off the top. Mathematicians love spotting patterns, proving them, then abstracting them, repeating until eventually they reach category theory. It's the kind of black hole of mathematics, I suppose. Its gravitational pull means that eventually we will all end up learning category theory. One for another day. Right, take care everyone. See you. I'm ending the live stream now.